Okay, hi guys. From the training yesterday evening, I thought I'd give a bit more explanation to the FM modulator. I've had a couple of students ask me about this, very good questions, so let's go a bit more in depth in how it works. So the FM modulator in the training looked like this, and I've duplicated that on the sheet here. So this is the bit that we're talking about, and it's trying to understand how the varicap diode affects the oscillator to give you FM modulation. So just to recap on previous trainings, let me just bring this up on the computer here. So we started off with capacitors, and the construction of a capacitor is two plates, and the things that affect the capacitance are the size of the plates, the spacing, and the dielectric in between. Okay, so larger plate areas give you larger capacitance. The dielectric also affects the capacitance, and the spacing affects the capacitance. So the closer they are together, the more they influence the other plate, and therefore the more capacitance it will hold. So just drawing that out here, we've got a capacitor here which has a certain amount of charge. It's relatively small, but it's storing this electric charge. So we've got pluses on one side and minuses on the other. And obviously, as the saying goes, opposites attract. So these are actually pulling on each other to keep them in place. If we move to larger plates, there's more space for more charge to settle. So therefore, with it being bigger, you will have a larger charge held. With more surface area, there's more positions available for them to sit across from each other, and therefore they will fill up with more charge. So less charge with a smaller plate, more charge with a bigger plate. Moving on from this, we now have bigger plates, but also we're going to vary the separation. So the further apart they are, they store less charge, because if you think opposites attract, the further away they are from each other, the less influence they're going to feel from each other. So there's less of a pull between them, and therefore less charge is going to be pulled to settle on the plates. So further apart gives you less capacitance. Moving on from that, if we go closer now, they're close to each other, so opposites attract, and they're feeling each other much more strongly because there's less distance here. So you'll get a lot more capacitance, or a lot more charge, on plates that are close together. Okay, further apart, weaker, closer together, stronger. So that's just a recap. Let's now talk about the effect of capacitance on a circuit. So we mentioned before we have parallel tuned circuits, which are L and C, and we have the series tuned, which is L and C as well. We've got the inductor, which is the L, and the capacitor, which is the C. And we know from that training that, let me just find it on the system here. With the training here, if you increase the value of the inductor or the capacitor, this reduces the resonant frequency and vice versa. So what that means is increasing the L from 1 millihenry to 2 millihenries, making it a bigger inductor, or increasing the capacitance, say from 100 nanofarads to 200 nanofarads, making these values bigger, will lower the resonant frequency. So by making these bigger, let's say the resonant frequency was 8 megahertz, making them bigger might drop it to 7 megahertz. We're going down in frequency as these values get bigger. Okay, so they're opposite to each other. Make these bigger and the frequency goes lower. Alternatively, if we reduce the value of L and C, make them smaller, this will raise the resonant frequency. So if you want a higher frequency, you use a smaller capacitor or a smaller inductor, or both. You can vary both at once as well. So this is the diagram drawn out that we had earlier. And again, just to reiterate, This is the oscillator circuit that we saw in the oscillator section. It's an LC oscillator with the L and C on the left hand side there as you look at it. And this is resonating at a certain frequency, let's say 7 megahertz. If we make L and C, or L or C, bigger, that will lower the frequency. Okay, as we adjust them, because they're adjustable, if we make the value bigger, that will lower the frequency. So as L goes bigger and C goes bigger, the resonant frequency coming out will go less. Likewise, if we make these smaller, the resonant frequency will go higher. Now, how can we do that automatically as we talk? Well, we've added on this part of the circuit here, which is very simple. We've got the audio in, we've got the varicap diode, and the other bits really are just here to make it all work. We've got an RF block, so RF doesn't come out the back. We've got a DC block, so the DC that's giving the varicap diode its voltage, again, doesn't interfere this way. So don't worry about those for now. Really, the key thing is audio in and the varicap diode and its capacitance. So what does audio look like? We know it's a voltage value that goes up and down. So the voltage would be the height here. Focus, there we go. So starting off at 0, everything is normal. As the voltage goes to a big value, so we're now at a high voltage value, this affects the varicap diode. And how does it affect it? Well, what the voltage does is, if we're looking at a diode, it's made up of two doped silicon pieces together, and if we put a positive voltage on one side and a negative on the other, it will be pulling the positives and negatives to the edges and leaving a depletion layer in the middle. Okay, this depletion layer is effectively the plates of a capacitor. This is how the capacitance is created. So as the voltage goes up, it pulls the gap wider, and therefore the capacitance decreases, because we've got a larger gap here, as we mentioned at the top here. Larger gap, less capacitance. Narrower gap, larger capacitance. Okay, so as your voice goes up and down, as it goes up here, we're going to see a decrease in the capacitance. As we know from the previous section, a reducing in capacitance will raise the frequency. So if this is resonating at a set frequency, as we get a peak in the voltage from the audio in, we're going to see a reduction in frequency, a reduction in C and a raising of the frequency. So what does a raising of the frequency mean? It means it's bunched together tighter. So as your voice goes positive, we're going to see a bunching up of the frequency. It's then going to come back down to normal, so we go back to this regular spacing. And as we go negative, the opposite's going to happen. As the voltage goes down, we're going to see a narrowing of the gap. Okay, so instead of being normal, it's going to get narrow, and this is going to stretch out the frequency. It's going to lower the frequency, because as the value of C increases, the frequency lowers. Okay, increasing the value of C will lower the resonant frequency. So lower frequencies are spaced out more, aren't they? So we've got low frequency, we've got medium or normal, and then we've got high frequency, which is a lot closer together. Okay, low, standard in this case, and then the high frequency, which is here. Okay, so that's how it works. As the audio is going in and out, this positive and negative is going to squeeze and stretch the capacitance, if you like, inside the layer, and therefore it's going to raise and lower the frequency of the oscillator as in time with this. Okay, it's directly affecting it. So I hope that clears things up, and hopefully those principles we've learned in previous tutorials will help you to understand what's going on here. It will start to make sense in the grand scheme of things. If you have any questions at all, feel free to leave a comment, and I'll see you in the next one.